systems. So we go through a quick introduction to the subject, and then I will focus on really two aspects of this, mainly the multi-cloud channels and our own utilization of that wireless network channels, along with presenting the main components of the system architecture, and if we have time, some testbed demonstration at the end along with the conclusions. Okay, so cognitive radio, that's a relatively new wireless paradigm. It's cognitive because it has the knowledge about the radio frequency environment, which is local to the user. This includes, mostly the frequency bands which are not occupied or underutilized in a particular area where currently the user is with his terminal equipment, or let's say mobile terminal. And by exploring this option, it's possible to switch with that frequencies for at least to stay always on, or to get some quality of service improvements or smart network access, and all this is done through the software defined radio configuration. So in a sense, by this we're getting some spectrum usage efficiency benefit. You know that the spectrum is a scarce resource, and the effective use of this is very important. That's why one of the solutions in this regard is the cognitive radio. Of course, all this reconfigurability and adaptability is done through adaptive software, which is able to meet the networks and users' demand, especially the user, which is considered as a consumer. So we're focusing on the user from the point of view that he is consuming different types of services, not only network communication related, but also application services. So this has the potential to redefine the existing wireless services, which is pretty much owned by the cellular operators, which having the consumer by different type of contracts signed for different periods, and by doing this, having him or her using only its own services. Well, here we have the ability to download third-party software to the mobile phones in order to provide some additional benefits from the consumer, for example, reducing the cost of the monthly bill. And everybody knows that, say, if you make a call through the free Wi-Fi, wireless LAN connection, through the internet using voice over IP, technology is much cheaper or even free to use than through the normal cellular network. And this was known for years, now more than 13 years. You can see that there was possibility to equip the mobile phones with such Wi-Fi ability, which means seamlessly through switch from cellular to Wi-Fi and vice versa where it's possible. But, for commercial reasons, this was never done, or if it's done with very reduced abilities. So the potential here that cognitive radio presents, maybe in the near future, is that the spectrum which is available could be shared without instructions from any network, so the user is not bound to any particular access network, and by doing this he is not paying any relative fees based on contract. So here is an example of how this could be done if the cognitive radio has its full potential done. Say the user in the morning on his way to work is starting a call with a colleague, but he has to leave his own home, so he's using voice over IP, some kind of application from the mobile phone, and using the Wi-Fi connection to his own home, which is free, of course, but then he's moving away, the signal is weakened. So if he has some agreement with the neighbor, he can switch to the neighbor's Wi-Fi, And then if it's far away from the neighborhood, maybe at some point he will need, to continue the current session through the wireless cellular operator, but just for a short period of time, and maybe not pay, but in exchange of some services in the future. And then continuing into the city, using basically any possible opportunity to switch to some of the existing infrastructure networks, say utility network, or this is the working, the corporate network. If, of course, this ability is provided on the mobile phone, and also if the mobile phone has the ability to switch to different frequency transparently without interrupting the user session. So, of course, with all the support in the hardware. So by doing this, the user basically, or the mobile phone, the user's mobile phone, will explore the frequencies of these wide spaces, which are not currently in so much use, or nobody is using them at the moment in the current location, which means by doing this, he may gain the full capacity or the maximum data rate available in that particular frequency band. And then moving to another location, he can switch to another frequency and so forth by hoping he can complete the current session. Moving to the military domain, even there is a very good potential here, because in this domain, the main thing is to deliver the message on time, whatever the cost. So all available options should be explored and utilized, which means in this case only the frequencies which are not jumped by the enemy, let's say, or free or use, and then switching by intermediate devices or nodes to other frequency bands and so forth, just to deliver the message of what the commander said at that particular moment. So talking about the radio, that's the radio frequency spectrum, which is from 3 kHz to 300 gigahertz. And of course, in each country, this is an asset which is controlled by the relevant bodies, like the United States Federal Communication Commission. And the spectrum is divided in different bands, as you know: very low frequency, medium frequency, high frequency, very high, ultra high, super high, and extremely high frequency. And you can see different sub-bands which are given for different type of services, which were shown on the previous slide. But the thing is that these frequencies are not used all the time. In some locations, there could be, let's say, less number of users currently active or none at all. Particularly, that's the case of the digitalization of the TV. So when the switch was made, the thing is that the digital TV channels, they are shorted and analog. That's why a lot of frequency bands were left empty, like white spaces, so this is known as TV white spaces. And in many countries, a map is made for particular regions where these frequencies are available for new type of services, of course, under the governance of particular communication body in that country. So the cognitive radio systems then could be the solution to cope with the continuing growth of the mobile traffic. As you know, it's a tremendous problem to the mobile operators, and to improve the efficiency by providing additional flexibility for this spectrum usage. Of course, there are many technical challenges. That's why we expect, and this is happening not overnight, but gradually. So basically, each cognitive radio system consists of 3 components. The first one is to obtain knowledge about the environment, different states, policies, user patterns, and user preferences, and then to use this to make particular decisions. Let's say to switch to another frequency band, to reduce the transmitting power in order to reduce the interference and so forth, which means to make some adjustments to the current operational parameters and protocols in use. And the third component is the self-learning, which means by using the experience, the past experience, to improve itself in order to get better performance in the future. So now considering quickly each of these components in a little bit more detail. So obtaining knowledge about environment, two different environments, radio environment and geographical. So talking about the radio environment, the status of the spectrum usage, the existing radio systems, the assigned frequency and bandwidth, which means in the current area to know which frequencies are available, and if you're using them, what interference level to expect. And then talking about geographical environment, the positions of the CRS nodes and other nodes, orientation and characteristics of antennas, distribution of users. Distribution of users is very important because if you know this parameter for each particular frequency, you know what to expect, what kind of average data rate to expect, because if there is potential for high data rate in particular frequency band, but let's say there are 100 users, probably it's better to switch to another frequency band where there is only one user and the data rate is not so high, but you're getting much more at the end. Okay, knowledge about the internal state of cognitive radio system nodes. So we're talking here about configuration as regards frequency bands and communication protocols, the traffic law distribution, and other operational parameters like status of the nodes and the transmission power levels. The external elements, this means nodes of the other radio frequency systems which are deployed at the area, the operating frequencies, coverage areas, positioning nodes. This is very important in order to get certain quality of service parameters, which is very important for each particular application which is run by the user on his mobile phone. And establish policies, because there could be a frequency available next to the current frequency band that maybe is not allowed to be used, because the interference that will may cause to the primary users will be much higher than it's allowed by the particular body. So, or if it's allowed, then they said what kind of maximum direct transmission power you can use in order to reduce this interference to the primary nodes. So, by using the frequency band and the adjustment underutilized frequency band, the computer radio system nodes are operating as a secondary nodes, so they should not cause any harmful interference to them. Okay, and the knowledge as regards the usage patterns, which means the behavior of the users primarily. The user needs, because depending on the application, as you know, some data sensitive, others are time sensitive, and for this we have different quality of service parameters as regards the average data rate, the minimum allowed, the maximum allowed delay, jitter, and so forth. So for each particular application, if a decision is made to switch over to another frequency, the decision should be justified and all the QoS parameters should be met, otherwise it shouldn't be done. Okay, so these are the approaches that could be used for obtaining this knowledge. First, it is possible to be done by radio link or network quality assessments. This is by using standard parameters like RSSI, received signal strength indicator, or signal to noise interference ratio, and so forth. The second approach is to have a dedicated wireless control channel over which information about this knowledge is sent by other nodes called a centralized entity. Spectral sensing, this is an approach which is done by the end nodes themselves to sense the spectrum in order to find out what frequencies could be used. Geolocation is usually used in combination with the database usage, because for each particular point on the map, from a centralized or distributed database, the nodes could retrieve information about the operational parameters, available frequencies, policies, etc. So everything basically in one go, and then use it for their own benefits. And collaboration between the nodes, of course, is also a possible approach, say by listening to the beacons of the Wi-Fi access points or whatever radio access technologies, or a combination of all of this. So in my talk, I'm covering in great details the wireless control channel approach, because we also did some work in this regard. So that's a dedicated channel where information is received, sent and received by other nodes as regards the environment, the operational parameters, and so forth. And the two main approaches use a cognitive control channel, CCC, or cognitive pilot channel. The difference is that in the cognitive control channel, it's a distributed approach. Okay? That's a channel which could be used by the computer cognitive radio system nodes to exchange information in real time between each other. Spectrum usage rules, policies, etiquette, availability, etc., etc. The other approach is more centralized. A central entity is gathering all this information using different methods, and then is distributing this to all interested nodes, either on request, so by using pooling, or just pushing this information, broadcasting this periodically to all the nodes in the current area. Okay. So I will return to this point later on, okay, and show you more details on that. Now, just to complete with the other two key features of the cognitive radio systems, the second one is to adjust dynamically the operational parameters and protocols of the system, and this should be done without user intervention, which means transparently to the user as much as possible. The user should probably not notice that something happens, so in the middle of communication session, say in the middle of calling and having a talk with someone using internet, telephony, voice over IP, this should happen. Like changing the radio access technology, adjusting the radio parameters, adjusting the transmission power and so forth, just to be able to complete the call with the required call to service parameters. And for all these adjustments, of course, is possible by reconfiguration, like software-defined reconfiguration, changing the frequency bands of the operational parameters. It responds to control commands, and all should be done to support the user preferences. So if the user preference is to complete the VoIP call with the minimum cost, okay, or zero cost or whatever cost, this should be desired. Okay, and the third key feature is learning, or rather self-learning, because some machine learning algorithms are employed in order to use all the gathered information from the past, the experience gathered so far, in order to develop some new modifications of the existing algorithms, or even new algorithms and models to cope better with similar situations in the future. So this is mostly in the computer science area, as you could imagine. Okay, so now focusing more on the cognitive pilot channel concept. The idea is very simple. There is a channel, either physical or logical, which provides all this information that cognitive radio system node may need. Say we have a mobile terminal or a user which is in completely known location, say in a foreign country. You don't have any information about the existing kinds of networks. You don't, in this case, you don't listen to any beacons, okay, like the current approach. So, but you have the support of this channel, which means after the terminal is switched on, it first detects the cognitive power channel available in the current area, synchronizes through that, and then start receiving advertisements about available access networks in the area, along with their parameters, frequency bands, manipulation techniques, and so forth. So all this is then transmitted, pushed to the mobile terminal. Actually, it's pushed to all terminals in that area using broadcasting. And then the terminal is using this information to choose the best, whatever best means, access network according to the user criteria for this particular communication session, optimized for time, situation, location, so we say optimized for the current context. So the user in this case is choosing this access network and then synchronizes, joins the network, associates with the base station and starts using its communication services. After that, periodically, the mobile terminal may continue listening to that channel in order to find out some changes in the environment, because any change in the environment may need relevant countermeasure or action as regards the configurability. As regards the deployment options, there are two for the CPC channels. Outband, which means a separate physical channel out of the normal radio access technology bands, is established and operating. And in-band, where the CPC is logical channel, it's part of the radio access technology in a particular area. As regards the operational mode, the channel could be the push-based, which means using broadcasting from the central entity down to the mobile terminals, only downlink is in operation, or pull-based, which means on demand. Whenever the mobile terminal needs information, just asks the central entity, so both downlink and UL, so not used to memory, obviously, but uplink communication. Okay, and in this regard, here I will present shortly the wireless billboard channel. It's our type of channel, which is actually the idea was conceived by us with Dr. Roman a few years before the CPC channel, and has a much broader context. So you could say it encompasses the CPC idea, because of this kind of channel, you can broadcast to users, proactively, push-based in background all information about the existing access networks and their operating parameters. So the same as CPC channel, but on the top of that, you can also broadcast information about other application-level services, which we call teleservices. Like, for example, the existing voice over IP support in the area of new operators or new mobile applications and so forth. So, in this regard, the WBC, by acquiring information about access networks, is operating actually as a downlink outbound CPC. This is much more than that. As I explained, this is a simplex channel, broadcast, not so much bandwidth is needed, so could be an outbound channel, but the coverage area should be as much as possible. And this is very important to be operated by non-access network provider service in order to create dependency of the existing network operators. And you can imagine that there could be different versions for different areas. Could be a local wireless billboard channel, say in a particular area like a university campus, which may provide information for guests and visitors about the available, say, Wi-Fi hotspots, info station-based services, and all services which are related to the university, how to find them. So actually the information is practically pushed to the mobile terminal to that user, and is matching its own profile. For example, it's a lecturer, visiting lecturer, say, in the Department of Electronics and Computer Engineering, will get only service related to that department, not about languages. And then there could be regional, national, WBC, with much higher footprint, or even international. But this all depends on the realization. Okay, so the main part of this WBC operation is the so-called service advertisement, discovery, and association. So it's a mechanism which could be used to push information. So service advertisements about the access network communication services like the CPC channel, and on the top of that about this application level services. Other protocols are already in existence that are using the idea of central registry of service descriptions. So each service provider, in order to have information about its own services broadcast or distributed to clients, registers its own service with this registry, and then clients using query response mechanism of some kind to query this registry and get the information they need in order to use that particular service. Now, in relation to WBC, the difference is that it's a simplex, so a unidirectional channel, working only from the point the direction from register to the client, which means no query mechanism could be done. So the only possible implementation would be the push-based one. So broadcasting periodically all service advertisements about all existing services in that particular area, including communication services, to that terminal. So whenever the terminal tunes to the channel, it should be able to get information about that. So now the key element here is how to, of course, schedule this. So is there any difference if the service is a popular one or not popular one? But this is all part of the implementation. As regards the carrier technology, of course, it is much better if some kind of broadcast technology is used, like digital audio broadcasting, DAB technology, or digital video broadcasting technology, because in this case, the terminals already have facilities for that, and if the channel is realized as a logical channel part of that technology, simply by turning to your favorite radio, your terminal is also gathering information about available services or services that you might be interested in. So many different such technologies exist, terrestrial, satellites, high altitude platforms. So we pick up two of these, initially the digital video broadcast for handheld, which is a technology of broadcasting digital video to mobile terminals, and then we have also realization of TDMV, terrestrial digital multimedia broadcast. And without going into too much details, what we have done is a three-layer architecture, where the layer on the top, the broadcasting layer, we realize as a carrier-independent layer, so whatever the technology, the same layer with the same implementation could be used on the top of the existing technology, whereas the other two layers depend on the carrier technology. So in the test bed that we developed, we have the DVH realization of these two layers. So basically the link layer is working as interface between the top layer and the physical layer on both sides. Okay, of course the main focus was to realize the top layer, the service layer. So we divided this into two sub-layers, application enabler sub-layer, where we have all the techniques of collecting the information about the service, available services, then clustering them, shadowing for broadcasting over the channel, indexing in order to find faster the information that the user might be interested in that sequence, and so forth. And then in the bottom we have the service enabler sub-layer, where you have basically the protocols used to deliver this information to mobile terminals, where we have our own realization of this protocol for this particular case. Okay? And one particular problem that we tried to solve was what kind of broadcasters, either flat or non-flat, So the idea here is to minimize the average access time, the time spent by the mobile terminal on the channel before finding the information he is interested in. And for this, our research showed that it's better to use non-flat broadcasting. So basically, to broadcast the services that are more popular more frequently on the channel. So in this case, we increase the chance of shortening the time getting the information about this particular service because it's broadcasted more times. So, and then on the top of that, we combine each services together in a group. For example, all voice over IP services in one group. So if the user is interested in doing a voice over IP now from here in Ireland, say to Bulgaria or to the United States, he just needs to, enter the phone number, and the system should be able to suggest mobile app, which is best according to the user's preferences. Say the user is interested in making a zero-cost call, then a particular application will be found that provides this. Okay, and the call is from the mobile phone side to another mobile phone somewhere in the other part of the world. Okay, then for actual data scheduling, we use modification of this very popular broadcast disk algorithm, where we modified it in order to get better performance. So the basic idea of this algorithm, just to show you how it works, is that services with different popularity are put on different disks. Each disk has different rotation speed, and on each moment, only services on the top of each disk broadcast on the channel. So in the first moment, we see we have service 1 for disk A, service 2 from disk B, and 4 for C. Then this rotates, okay? And till the next moment, this A will make one full rotation, this one will make half rotation, this one will make quarter rotation. So now we have 1, 3, and 5 on the top, and the next moment it will be again 1, but with 2 and 6, and then finally 1, 3, and 7. So you see in the completed cycle, we will have, as a result of this, information about service 1, the most popular, distributed, broadcasted 4 times, where for the less popular, 2 and 3 times, and this just 1. Okay, so we worked with that algorithm. We further decided to split the services into so-called cold signals, so not so popular services, and hot services, and we use mostly modification of that algorithm for the hot signals, for the hot services, in order to decide what frequency each of them should have as regards the broadcasting. And then we work also on indexing. And the main idea of indexing is to reduce the tuning time. Okay, so not to spend a long time listening to the channel before finding the actual information. Let's say if the mobile terminal tunes at this moment, it is interested, let's say, in service description 7, 4 is currently on here. So the mobile terminal reads from somewhere when the index will be broadcast, then tunes out, waits for the index, then tunes again, reads when exactly what moment the information that it is interested in will be broadcasted, and then tunes out again, and then exactly that moment it tunes in, reads the information about service 7 and uses it. So by doing, by implementing techniques like this, it is possible to reduce the tuning time, and as a result of this, you save battery power. But the disadvantage is that we increase the access time. So you need to find compromise, and we develop our own algorithm. So without going too much details, but as I explained, we group the services into segments, and each segment will have services of the same or similar type. So let's say it's a voice over IP services, And then the front of each segment we have inner index, which shows where each service information about this solution will be broadcasted. And then also we have inter-index about the individual segments. Okay. Okay, and this is the software architecture that we developed, the Java-based multi-agent system, which uses, as I said, DVBH as WBS carrier. And this is the test bed that we developed, and we get some good results, which were published. And also, information about this type of channel was taken on board by the ITU in these reports as implementation example of the CBC, piggyback on broadcast digital platform first, and then as an example of wireless control channels. This was done in 2014. Okay, and now just to finish with the expansion of this idea by developing it more as in the direction of application level services that the user is actually interested in, and pushing information about this to the user depending on his own preferences, depending on the service characteristics, and depending on the network parameters, available access network at the moment. So the context. And this is what we call always best connected and best served paradigm. And we built, architecture where we use the standard approach where client application, client mobile app is getting information about user behavior as regards the services that user is mostly interested in, and this information is sent to the system. It is processed by the use by the help of the cloud computing technology. As you can see, this could be used as an input to the WBC because, as you remember, the non-flat broadcasting is based on the user interest. So from here we're getting this information. And also, here, as a feedback, we're sending personalized recommendation for particular services for that particular user in that particular moment, so for that particular context. And we are currently building this system as a cloud-based one using the standard cloud computing technologies like Kafka, Swarm, HDFS, and so forth. So all this is the current work of our team. So this was very short, I think, introduction into the area. It's a very promising technology, as you can see, but there are also many technical challenges because it's not so trivial just to switch to another frequency. You need to have also support in the higher communication layers as regards to handover the service, session continuity, and so forth and so forth. And also everything depends also on the ITT radio regulations and both international and national in each country as regards each particular frequency band that might be available or not. So that's all from me, and now we'll be very happy if you have any questions to answer them.